Okay. And we're going to continue. We're going to continue with work, picking up where we left off. Finally, we're doing some workarounds, right? It's not going off too long. Okay, so problem 3 and 4 sort of builds on problem 2. So I probably have to run over problem 2 again quickly. So we get the idea. So at a very tall building, there was a 100-foot cable hanging off the building. So this was 100 feet. Cable weighs, once you start talking about weight, you should know that that's a force. So you should expect pounds or something similar, pounds or newtons. Weighs 300 pounds. This means it's 3 pounds for every foot, right? You'd assume it's a uniform cable. So each foot, so 1 foot of the cable weighs 3 pounds, 2 feet will weigh 6 pounds, and so on. And so if you have delta x feet, it weighs delta x times 3 pounds. And so this means delta x feet of this cable would weigh delta x times 3 pounds. Okay, so we had that. And so the idea was when you're pulling something, work when you're just lifting up an object and putting it somewhere, that's sort of easier to calculate. But in the case of the cable, what's happening is the thing you're lifting is changing in weight while you're lifting it. So you're lifting it in pieces. And so you sort of dissect it into pieces and then figure out what is the work to move each individual piece, right? So we set up a coordinate system here where I say the piece I'm moving is at a height x from the bottom. The distance it would have to move to get to the top would be 100 minus x. And I took the length to be some small infinitesimal length of x, which is delta x. And so the work to move that one little slice was going to be force times distance. The force is of course the weight, so that's 3 delta x, and the distance we found was 100 minus x. So that's 3 times 100 minus x times delta x. And so now to find the total work, we add up all these guys, but to do that, it's basically forming a Riemann sum, where your delta x would then become the dx, the differential, and we integrate along the length that we want to move. We want to move all points from x equals 0 to the point where x equals 100, the entire weight, and so the entire cable. And so we set that up. We didn't compute it because I think that would be easy to compute, and 15,000 was the answer there. And so that's sort of the setup for problem 3, right? So we have the same cable, but now we attach a bucket to the end of the cable. So we're actually pulling something to the top of the building. So someone puts a bucket of water at the bottom, and we want to pull it to the top. And it has 500 pounds of water in it. The bucket, at this point I said it has negligible weight, meaning you can ignore the weight of the bucket in the problem. So that's what negligible means, you can neglect it. And now you want to do, the idea is to pull up the cable with the bucket of water to the top of the building. And so how do you think you would approach this? Yeah?
So this, because you've got that constant weight that doesn't really change.
Yeah.
So you've kind of got a situation where you need an integral and then when you don't.
Yeah, it's just going to be a force times distance kind of thing. This is just a mass that weighs 500 pounds that you're moving from location 0 to location 100. We know the work for that. So the idea is when you look at work, how you would start out, let's pretend you didn't even do part 2. How you would start out is you would just break it up into components. There's the work to move the rope or the cable. For the cable, plus the work for the bucket, plus the work for the water. Now we're told this is negligible, so that I'm going to ignore. The weight for the cable is what we would set up in exactly the previous way. Plus, now the weight for the water, I would literally just do force times distance. So this would be 500 times 100, because I'm doing the work equals force times distance. Remember what we said is as long as our force is constant, which in this case it is, that interpretation of work is good enough. Just do the force times the distance. So you just do the integral part and then you add that part. So it's like we're just adding something to our answer. And so it ends up with 65,000. And by the way, that's the idea that would have helped you with the second bonus problem. So the idea in the second work bonus, I forgot, this is maybe problem 3 on test 2. The idea is when you were pulling up half the cable, right, so I think, was it 100 feet still?
Yeah.
Right, so it's 100 foot of cable, but you're only pulling up the top 50 feet. Right? So the way you would conceptualize that is I'm really pulling up a 50-foot cable, and then there's just this mass hanging on the end of it. And so this here is, let's just call it a mass. So just a thing that you're moving by 50 feet. So the work here would be the work for the cable, plus the work for the mass at the end. So you think of a part of the cable as just this weight that's hanging on it that you're moving. And so that's going to be force, that's going to be force times distance, which is, in this case, it would be 50. And then here you'd set up an integral blah, 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 dx. So it would be the integral that you set up from the previous part, from the previous bonus problem, except here you'd go from 0 to 50 instead of 0 to 100. And then you're going to add the work to move this mass from here to here. So that was the idea. I mean, I'll write out a full solution when I'll post the full solution online, but since this idea is what we're using, that was the idea. You took the cable, but you split it into 2 parts. A part of it you consider it being the cable that you're pulling up, but the other part is just a mass that you're pulling up. And it's not, it'll always be hanging off the side of the building, and so I can take this guy. Let's move on to problem 4. So it's another variation on the same problem. What if the water is leaking out of the bucket, right? So the bucket has a hole in the bottom of it. So someone pours 500 pounds of water in it and you start pulling it up, but the water is leaking out, right? And basically you want to go complain to just say, you know how much work I did to pull up this empty bucket? And here's how much work, let me calculate it for you. I did this much work. And you can complain with some data. So now we want to know how much work did you actually take you to pull this up. And the water leaks out at a constant rate to the point where by the time it gets to you, it's completely leaked out, right? So it was filled with 500 pounds at the bottom, but by the time you pull it to the top of the building, the bucket is empty, right? So, and the water's leaking out at a constant rate. Okay? So now we want to know what is the work that we were doing to pull it to the top of the building. So there's their cable. And there's a bucket here, but it's leaking. Okay, so that here, from here to here, we're still looking at that length as being 100 feet. I'm still going to let this be x equals 0. We do exactly the same setup to do the cable part. So that's 100 minus x. This here is delta x. Let's focus on the bucket for a while. Well, the water in the bucket. How do you think you can actually set that up? Because the force isn't constant anymore. It's not just a constant 500 pounds. So how would you actually deal with that situation, where the bucket is leaking? So you sort of go back to the basics, and you have this idea that work is an integral of force. Would you be able to find a formula for the force exerted by this water? What do you think? What does leaking out at a constant rate hint to you?
Isn't it like, what were those problems before, was like a cylindrical hole, and like, the difference is like dV, dt or something? So,
No, the related rates problem? No.
no, okay. Then,
You'd only do that if you were asked to find a rate. Then you'd kind of think that's it. But here we're asked to find work, which is not a rate. So we wouldn't do that setup. The time actually doesn't matter, right? When we talk about work, it doesn't take, we don't care how long it takes you to do the work. We just want to know how much energy was exerted to move this object from one point to another. Like how long it takes is irrelevant, so don't focus on the time too much. But the fact that it's leaking out at a constant rate gives us some sort of model that we can piggyback on, right? What kind of model do you know has a constant rate?
Straight line.
A straight line. Right? That's the quintessential thing. You hear a constant rate, you think, oh, straight line, that's a function that has a constant rate of change. Right? Which means there's some way to actually think of the water as just a function of a straight line. Okay? How would we sort of construct this line? So let's say here, of course, the important things are the force and the distance. Right? So let the x-axis be the distance, and I will let the y-axis be the force. Now when at position x equals 0, what's the force? 500. So on this line, there's a point, 0, 500. Now it's leaking at a constant rate, but again, the time doesn't matter to us, so time is not something I'm considering on these axes. I'm thinking of just matching the distance with the force. I know that eventually I will get to a distance of 100, and what is the force now? Huh? 0, because the water is completely leaked out. There's 0 pounds of water at that point, which means I can conceptualize the force exerted by the water as this particular straight line. So here, f of x would be, what is that going to be? Clearly it's going to be 500, because mx plus b, the plus b is the y-intercept, so that's going to be the 500. And it's going to have a negative slope because it's decreasing, and what is the slope? It's rise over run. Right? So 500 divided by 100, so it's minus 5x. And you can double check that, realize that when x is 0, I have 500. If I plug in x equals 100, I get 500 minus 500, so that actually works. So it turns out that I can think of this formula. This is the weight of the water in the bucket. And so now I can get to computing the work. So now we can do the work total is going to be the work for the cable plus the work for the bucket plus the work for the water. Weight of the bucket is negligible, so there is no force. The weight of the cable, we've actually computed, that was 15,000 foot-pounds, and this was previously computed. And now, for the weight of the water, I will set up this work integral. Work is the integral of force. So I'm going to integrate this function, 500 minus x, minus 5x. And x goes from 0 to 100. Real quick. And you compute that. And again, the integrals aren't very difficult here. I think it ends up being 40,000 total. Right, the setup is the main thing here. Usually with these integrals, what you're actually integrating won't be difficult. It'll be some sort of polynomial or something. So, and of course, if now they told you, oh, the bucket has a weight. Let's say the bucket itself weighs 50 pounds, and then you just put work, force times distance, just do 50 times 100 and add that to it. So the idea is you just dissect it into different pieces, right? Dissect when you're moving a single mass all at once versus some sort of elongated mass piece by piece versus something else. So the idea remains the same. You're still using this integral, but how it applies to different objects would be different. Let's move on. That was the last example in the lifting and pulling problems. Let's do some pumping problems. Yes.
Sorry, couldn't you have thought about the bucket as well instead of creating a force by distance? Couldn't you have thought about it as the pulling cable but in reverse? Because when we were pulling the cable, what we ended up having was 3 times 100 minus x because of the distance of the cable going up.
Yep.
In the same way, you have the water going down at an infinitesimal point, and so you'd have 5 times 100 minus x, and then you'd still end up with 500 minus 5x instead of things go that way.
Yeah, that would be correct.
Okay.
I don't know many people would think of it that way. Let's imagine the water as a rope. But technically, yeah, it's the same principle, right? You're lifting something in pieces, except in this case, the pieces aren't being pulled up; they're falling off.
Right. So as it.
But you sort of think of it as an opposite problem, and yeah, you could get to it that way, but. That's super abstract. I don't think that's typical to think of it that way, but it's not wrong to think of it that way. I mean, but that's probably the way a physicist thinks. We're writing physics. Yeah. Let's imagine this horse is a sphere with no friction. You know, and it's on a frictionless surface. Sure, Mr. Physicist. Let's imagine that. Yeah. What if the water were a rope? Yeah. Bit too abstract for me, but not wrong. So now we're going to do pumping problems, and we're going to see how to conceptualize these. So the idea is here you have a tank of some sort, there's liquid in the tank, and you want to pump the liquid out of the tank. And you want to calculate how much work, which is connected to how much energy you need to have this done. Okay? So here, now I wrote out this formula here, but it's basically me rewriting the previous formula. It's the same idea where we're doing work is the integral of force. And remember that this kind of represents, of course this represents the force, where the dx is kind of representing your distance. And the idea is here, is when you're talking about the force of a liquid, you could, or almost anything, you can think of that as the volume times the density, right? But you make sure your density is in units of force. Okay? So remember the density, a little bit of chemistry there, if you remember density, right? So that's just how much stuff there is per unit volume, right? So if you tell me the total volume and you know how much stuff there is per unit volume, you know how much stuff there is overall, right? Now if you express the stuff as a force, you can make that computation, right? Tell me the total volume and tell me for each unit of volume how much force we're experiencing, and I can tell you what the total force is, right? But so for liquids, it's easier, for pumping, it's easier to conceptualize work as the volume times the density times the distance. But volume times density is really another way to get to force, right? So it's not a different formula. It's just, it's convenient to figure this out, right? So I can say, I have 100 gallons of this liquid and it weighs 5 pounds per gallon, right? Then that's you telling me the force, but it's in a different way. You're just telling me the force is in each piece, right? And so we can think of it this way, right? And that's sort of the way that's more convenient when you're looking at pumping problems. And again, I'm going to show you the setup. Again, as well, we're going to be doing a dissection, because if you're pumping a liquid, you're not moving all the liquid all at once. You're pumping it layer by layer. And so that's the idea that we're going to take here. We have a tank with some liquid filled in it, and we're going to think of how much is it taking to pump layer by layer out of this tank. So you're going to dissect this liquid into layers, and then figure out the work for each layer, which you can use this idea, and the integral is going to add up all the works for each of these individual layers. So let's actually see that in action a couple times. So this is problem 5. And these can be a bit more challenging because of the volume part. Right? Here's where you're going to have to remember the volume of various kinds of things. You remember how to find the volume of a cylinder and the volume of a rectangle and a box and things like that. So there's going to be some more geometry here. The density is usually going to be given. It's not something that you can really figure out. It's just, that's a scientific fact. Okay. So let's actually just jump into it. An inverted conical tank is filled with liquid of density 200 pounds per cubic foot. Right, so there's liquid, it weighs 200 pounds per cubic foot. It's a very heavy kind of liquid. By the way, for comparison, water actually weighs 62 pounds per cubic foot. Right? You take a cubic foot of water, it'll weigh around 62.4 pounds. But this liquid is a lot thicker, more viscous. It's 200 pounds per cubic foot. The tank has a height of 12. Right, so let's look at what we have here. So it's an inverted conical tank. I know the height is 12 feet. And I know the radius at the top, so the largest radius is 6 feet. Find the work needed to pump the liquid out the top of the tank. And we know it's filled with some liquid. Right, so the liquid is filled all the way to the top. And I want to know how much work will it take to actually pump all the liquid out. So the idea here is similar to the rope one. I'm going to think of pumping the liquid out layer by layer, right? So I'm going to slice it into infinitesimal layers. So there's going to be a point here where I'm going to choose one layer of water, or not water, whatever liquid to pump out. Now notice if I look at a layer here, it's really going to be some sort of disc with thickness, right? Because each cross section of this cone is going to be circular. Right? So when I think of a layer of water, that's what it's sort of going to look like. And again, I'm going to take the same principle. Right? I'm going to say like x is 0 here. Imagine that the layer I'm pumping out is at a height x, that its thickness is delta x, and its distance that we have to move to get to the top, we're pumping out the top, would of course be 12 minus x. So the same idea as the cable, we're slicing things and we're moving piece by piece. The difference is now, each of our slices will have a different size, so it's more general than the cable is. Right? Because at this level, the disc would be a lot smaller than at that level. Right? So the pieces themselves are changing in size, but it's the same principle. So now we would have work equals, work for this one slice of liquid is going to, I'm going to think of this as volume times density times distance. Okay, so now let's talk about volume. Do you remember the volume of a disc? Volume of a disc. Well, pretty much the volume of a cylinder, right? What is it?
Pi r squared h.
Yeah, pi r squared times h, but in this case our h is delta x.
Right.
Times the density. The density we were told is 200, and this is in pounds. So that's a force, right? It's very important that our density is units of force. If they told us the density in units like kilograms, you'd have to convert it to force by multiplying by gravity. So you'd have to multiply by 9.8. But here it's in pounds, so that's already a force. And the distance here is 12 minus x. Now, at this point, an issue might jump out to you. It might not, but I'm going to raise the issue here. Does anyone see the issue?
Radius is changing as well.
The radius, right? Here is something that's an r. What is r? My variable is x. Obviously, the delta x is going to become a dx. I'm going to set up an integral in terms of x's. But there's this thing we can potentially write it in terms of x, but at the moment, we don't have it in terms of x. So this is some varying function. How do we get to the radius is going to be the idea, right? The fact that we have some other variable here is a problem. We need to actually work that out. So any ideas how to get to the radius?
Did someone else?
You go ahead.
I mean, because it's proportional to how you're changing the height, the change in radius is proportional to that. I think it's half, isn't it? Because you're going up by 1 on x, you're going out by half that on the radius. Because the diameter is the same as the height of the whole cylinder. As you move up the
Yeah.
cone. you
So that's the
half
idea.
out.
Any way to get to that? Maybe you were thinking of a more systematic way?
Yeah, I was thinking like make r in form of like x, but I don't exactly know what variables are.
So your reasoning is correct, but and if you can see it that way, you know, this is really twice the length of that, so you can imagine that they vary directly by a factor of 2, which wouldn't be wrong. A more common way that we do this is actually, I can show you here. You take a slice here. You'll notice that you formed a triangle. Right? So you do a vertical slice through half the bucket, through half the conical tank. And they can sort of set this up, which is exactly going to be your idea of being proportional, but they like to use a geometrical shape to show that. So the idea is here, this entire length here is going to be 12, this length here is going to be 6, here is going to be the radius of the current layer of water that you're considering, and the height here we know is x. It's x units from the bottom. And this is a similar triangle, and so we have proportionality. This involves similar triangles. So we have proportionality. Right, so just to put a math theorem behind the idea that you have here, some sort of weight. And so what we know now is this means that if I take the height over the base of the big triangle, it would be equal to the height over the base of the small triangle. Because corresponding sides are proportional in similar triangles, right? And so the height of the big triangle is 12, the base of the big triangle is 6, the height of the small triangle is x, the base of the small triangle is r, and so you get here that x is actually equal to 2r, which is basically what you were saying. Which means your radius, well, r is what I actually wanted to solve for. So r is going to be half whatever the current height is, right? And that's going to be consistent throughout the whole thing. And so I can replace this r with x over 2. So this means the work for this one slice is going to be equal to pi times x over 2 squared times 200 times 12 minus x times delta x, which means the total work. I'm going to do an integral here. Let's move the constants to the front. So this is 200 pi over 4 times x squared times 12 minus x delta x. And what are the x values that I care about? Well, the entire tank, so it's from 0 to 12. So the limits here talk about the length of the liquid. You want to move. Or it's in terms of the x values that you already set up. So the question could have asked something like, how much work is done in pumping the top half of the water out, right? The top 6 feet of water. Then you would go from 6 to 12, etc. And 5. So I'm not going to do that. Again, that's just a polynomial, so the integral itself shouldn't be crazy. But the answer here was, it's going to be large, 86400 pi foot-pounds. 86,400 pi foot-pounds. All right, you just distribute this, do the power rule, fundamental theorem of calculus. Right. But this idea would apply to all pumping problems. This is the concept we put on top of it. We just find the volume times the density. If the density is given in terms of mass, you would convert it to force by multiplying by gravity, and the distance. And again, you can figure out the distance just by setting up a diagram and sort of putting a coordinate system on top of it and measure the distances using the coordinate system. And once you can get that, if you show any variables show up here other than the variables you use here, you need to figure those guys out through some sort of geometrical meaning, geometrical idea. Get through one more problem just to sort of hammer home the concept here. So in problem 6, a rectangular tank has length 10 meters, the width is 5 meters, the height is 5 meters. So here our tank is a rectangle. The length is 10 meters. The width is 5 meters, and the height is 5 meters. It's filled with water, and they told you the density of water. Here, it's 1,000 kilograms per cubic meter. Find the work needed to pump the water out the top of the tank. So now here, filled with water. We also know the density is, it's water, it's nice, 1,000 kilogram per meter cubed, which means the density force is going to be 1,000 times 9.8, right? That's 9.8 meters per second squared, kilograms per meters cubed. So this is this just becomes 9,800, and this is kilograms per second squared meters. Which I think is newtons. But 9,800 is what we care about. So we're concerned about the. So we want to pump the water out the top of the tank. So again, we're going to use that idea, pump it in layers. So I'm going to choose a layer of water here that I'm pumping out. So let me say there's x equals 0 at the bottom. This is at height x. The thickness of this layer is delta x. The distance I have to pump it out is 5 minus x. So my work, I'm going to think of that as volume times density times distance. And this is the work for the small slice. What's the volume of this thing?
250.
50 delta x.
Right. I'm talking about the volume of the slice.
Oh,
So that's length times width times height. So it's 5 times 10 times delta x. So this is 50 delta x. Density we just calculated. This is 9,800. Distance is 5 minus x. So this means that the total work, I want to pump the entire thing, so it's from 0 to 5. Of 50 times 9,800 times 5 minus x dx. Here's what your delta x becomes. Let me throw that in a Riemann sum. This was 6,125,123 Newton meters. Or you can write that as joules. I don't care terribly too much about the units, but once you realize the units really help you with the setup here, you might have to realize that, oh, since they gave me in kilograms, I have to make sure that's in force. So, yeah. I mean, the others are similar. I think we've done about the 10%. Yeah, the other ones you're still going to draw, you're going to do the slice the same way. You know, the difference is going to be the volume and the density you're dealing with, but after that. So you guys can try those on your own. I can tell you the answers, and you guys can try them to see if you're getting the answers. But there's nothing else to teach, really. So for problem 7, answer is 400,000 pi foot-pounds. 8 was 405 pi meter-pounds. So try those. If there's anyone that's giving particularly a lot of trouble, we'll talk about that. We can talk about that on Friday. But I don't think in principle anything else is going to be everything.
What's the Friday topic?
On Friday, we're going to do parametric equations, which is going to help us with polar coordinates, and then we're going to do sequences and stuff.
Homework's gonna be due Friday.
No homework. But I do want you to actually start working.
So what about the homework from last,
Approximate intervals.
we finished the section last week, do you want that due on Friday?
Arc length.
Arc length? I thought we already handed that in.
No.
8.1, right?
Okay, so bring arc length up, right?
Yeah, so
That was a very short one.
Right.
But work might take some people a while to sink in, so I'll probably want you to work on that over the weekend.
So like
Might take some work to